All right, do you remember what the title was from the previous section of material? What the items were that we were talking about? Exponential functions. That's exactly right. And exponential functions and logarithmic functions, which is what we're talking about today, are very, very related. In particular, they're what we call inverses. So I want to talk to you about where logs come from, because it kind of feels like all of a sudden they just drop in out of nowhere, and they really don't. They come from this inverse idea. So if we were to take and try to find an exponential function's inverse, we would take the y equals b to the x. That's an exponential function. And then if we switched x and y, we would get x equals b to the y. That's what it would look like if we switched x and y. Okay, so the inherent problem in that is that what we want to do in solving for y is we need y to not be in an exponent, right? And everything that we've done so far has no ability to move an exponent out of the exponent location. We need to be able to move an exponent sort of down, if you will. Does that make sense? So what do? Well, we introduce this new term so that we have a way to express what we're wanting to do so that y can be down. And that new idea is called a log. So if we take a look, let me slow down just a little bit. So if we take a look at what a logarithmic function is, it is an equation of the form y equals log with this little subscript of b. That b is a subscript. X is on the same line as the word log. When y is equal, that's written wrong. It's a typo, sorry. That should say x is equal to b to the y. So if I have x equal b to the y, which is where we sort of left off on the previous slide, it can be manipulated to look like y is equal to log base b of x. Okay, so what I want to show you is, I don't know how many of you are sort of visual learners. Let me just ask you, who's a visual learner? Who looks at it and says, if I can see it, I can figure it out, but it's going to take me seeing something? I'm a visual learner. I have a brother-in-law who's super visual in terms of like keypads on doors. You ever see the keypads on the doors? He remembers codes to like the keypads on the doors by visually where he pushed the buttons for. When I was memorizing massive amounts of scripture as a teenager our denomination has something called teen Bible quizzing. I could tell you exactly where it was on the page. I could tell you if it started in the middle, the verse started in the middle of the page or on the left or on the right, because that's how visual I think. So for me, I'm going to show you a visual way to rewrite and to change these expressions around. In doing so, we're going to work from two directions. We're going to work from logs into exponentials, and we're going to work from exponentials into logs. And what we're going to do when we see something like log base 3 of x is we're going to draw a circle around the base. In this case, it's a 3. And we'll talk about what happens when it's other things later. And we're going to draw an arrow. This arrow is a curved arrow, and it looks like this. So it crosses all the way to the other side underneath the whole equation and back, landing right beside where the 3 was. And I had a student that I observed one time teaching this, and they called it they were a student teacher, and they called it a scorpion tail. And I thought, that's pretty appropriate. It looks a lot like a scorpion tail. And if you've never seen a scorpion, you can Google it later. But yes, they've been in my house. I've actually seen a scorpion before, many times actually. So, looks like this. So what does this mean? Well, the part where I circled is where I begin. And it starts as the new base of an exponential. And if I follow the arrow around to the other side of the equation, the next location that I get to is the 2. And that becomes the exponent next to the 3. And then I have an equals, and then I land back on top of the x that's right next to where I began. So I'm following the trail of the tail all the way around. And as I work my way around and I land at the x, I have the equation rewritten in exponential form. Obviously, this one could be solved. X would actually equal 9, right? Yes, it would. Sometimes you end up with enough to solve something here, and it's nice and whole numbery. Sometimes it's not. It just depends on the values. Now, it works the same way when you're starting with an exponential and going into log form. You're going to circle the base. It's just that the base of an exponential would be where this 5 is, whereas the base of the log is a subscript. And you still cross to the other side of the equation first, all right? My scorpion tail is going the other direction, and you land back to where you started. Okay, so this is going to be a log equation, right? I'm going to have log when I'm done. And the base, 5, is now the base of the log. So we call them the same thing, which is actually really friendly, right? A base of a log, a base of an exponent, it's the same place. So this is a 5 in this one. And if I follow the tail around over here, y is next. So this y comes right beside the base 5 on the same level or line as log. And it equals where I land. And what do I land on this one? X. Okay, being able to move in and out of log equations is going to be able to help us solve them, to graph them, to simplify and find, evaluate them, all of those kinds of things, which is what we're going to be doing for the next several class periods, is working with these crazy things called logs. Okay, a couple of things that you should notice is if you pressed the word log in your button in your calculator, most calculators, and at least all the calculators I've ever seen, don't give you an opportunity to put a number down here like the 3 or the 5 that we just saw. They don't do that. It just says log. So when you see just log written, it means that it has a base of 10. So there is an understood 10 down here. That's what your calculator does, and it's because we work in base 10, and I mean, that's the why. So it's called the common log. And then this other one where it has this ln. Well, the reason it has that notation is ln stands for natural log, and if you're familiar with any other languages besides English, most of the time in other languages, adjectives come after nouns. So we would say pretty girl, right? But in Spanish you would say girl pretty, okay? The adjective, the describing word comes afterward. So when you say natural log, you would mostly say in other languages log natural, which would be L and then N. So that's the reason for the ordering. Got that? So what does it mean though? Well, it means that it has a base of E. So this is equivalent to having log base E of X. Okay? And you see natural logs, base E, exponentials and things happen more naturally, like in nature, hence the word natural log. So that's where that's coming from too. Okay, so I feel like I've just thrown massive amounts of notation and descriptions at you. So we're going to do a whole bunch of examples now on how to manipulate and solve and simplify things. And we're going to do a little graphing as well. Okay, so the first thing we're going to do is a couple of rewritings. So the first one actually starts with ln of x equals 2. It's not line, by the way. Sometimes I have people say line x. It's not lines. It's ln, or you can say natural log more specifically. I usually abbreviate and say ln. All right, so when I look at this, literally what I do is the first thing I would do is I would rewrite it as log base e. And I would circle the e and draw my scorpion tail. The circled E is where I begin to rewrite. It's now the base of the base of an exponential function. And if I follow the tail around, what number or letter do I end up at next? The 2. So that will be the exponent on e. And then that equals x. Something else you can think about is that when you're rewriting these back and forth between each notation, whatever it was next to before, it's not next to now. Do you see how it looks like the e and the x are sort of next to each other? They get separated, and that happens every single time. If you think about it here, this one looks like the e and the 2 are next to each other. They get separated if I turn it back into a log. So that separation always happens. So on this one, another e, I'll circle the e, it's the base, and draw my arrow around. The arrow doesn't matter whether it goes left or right, it just needs to go to the other side. Okay, so if this is written with the equals and the e's on the left, the arrow is going to go to the left. If it's written like it is now, and it's the e and the arrow goes, and the number, sorry, let me say that again. If I have it written like it is right now, and the e to the x is on the left, then the arrow will go to the right. So whichever side it's not already on. Okay, so as we rewrite, this will become a log. Whoops. So I have log base e. What would come next? The 5, and it's on the same line as the log. Okay, e is the subscript, 5 is right next to the word log. And then I would put an equal sign, it would equal x. And I'm totally fine if you leave it like this, but just so that you're aware, this means natural log, so you could also write this like this. Okay, this is an or. Either of those would be ways to write it. Both of them are equally correct. The second one's just shorthand. Okay, if you have your calculator with you, grab it out. Next question is simply how we put this in the calculator. And we'll actually start with the one we just were on because we can. In your calculator, see if you can find the button that says ln. If you don't see it, flag me and let me help you find it. Does everybody see it? Okay, so if you were to want to know what is x on this problem, you can find it. Hit the ln button and then hit the number 5 and press enter. I have no idea what it is because I didn't do this one myself. But what do we get? 1 point, we'll do 3 decimals. What'd you get? 609. Cool. Did everybody get that? Did anybody's calculator give them anything different than that? Okay, let's try a different one then. Same kind of a question. Using your calculator to evaluate natural log of 3/4. You can enter that as natural log of 0.75, or you can enter it as 3/4 as a fraction. Sometimes you need to put it in parentheses. This one says to the nearest hundredth. What does hundredth mean? 2 decimals, good. So what would this be if you evaluate it to the nearest hundredth? Negative 0.29. Okay, so there's only 2 logs that your calculator will calculate directly. ln and log base 10. Okay? We will get to a point where I can show you how you evaluate log base 3 or log base 5. It's not especially difficult, it's just not in this particular lesson. Okay? So for right now, the only logs we're going to be evaluating are natural logs or common logs. All right, our number 4, number 4A and B. You'll notice that you have log with another base on part A. Part B is a little different, but on part A. And I just told you, your calculator does not directly compute this because it doesn't have the ability to plug in a base 4, right? So what are we going to do? Well, I'm going to show you how we can do this and how I will expect to see you do this. Okay? This equals something, right? It's a number. I mean, there's no letters. Log base 4 of 64, it's all numbers. And log just means operation. It's like saying square root, right? It's not a word. It's not a variable. It's an operation. So this has got to be a number. We just don't know what number it is. So for now, I'd like for you to say that it is the number, quote unquote, x. I just need to figure out what x is. Okay? And what we do know is that you can change this into an exponential form. That's what we did on the first couple of problems, right? Is we switched them in and out of logs and exponentials. So we circle the base, which is 4, and draw our scorpion tail around. So somebody tell me how I would rewrite this in exponential form. Four to the x, yep, equals 64. Okay, is everybody good with that? Here's the cool thing. 64 is 4 to a power. Four to what power is 64? Play with your calculator. What is it? 3. It's just 4 cubed. 4 cubed is 64. So what I'm trying to do, truthfully, is get the same base on both sides. So if the bases match and these two sides are equal, then what do you think has to be true about the exponents? They're equal as well. So this x that I sort of made up out of nowhere, we just solved and figured out that it's actually equal to 3. Good job. We're going to do part B in 2 ways. The first way we're going to do it is just like I did on part A. And then we're going to use the calculator to check and make sure we did it right. Because it's a really nice one to plug in the calculator because it is log base 10, right? That's great. But a lot of the ones you're working with won't be, and we want to practice this idea as well. So, same thing, we're going to put that this is equal to, and I'll just make up another letter today, A. So, what is the base of the log again? 10. So there's an understood 10 down here, and that's what I circle before I draw my scorpion tail, right? All right. So the 10 is the base of the exponential. What comes next? A is a power, and then equals 1/10. The goal is to get the bases on each side to match. I want to rewrite 10 to some power. 1/10 is 10 to what power? -1. 1 over 10 is the same as 10 to the -1. Are you guys good with that? So, again, my bases match. What does that tell me about my exponents? Not add them. What's that? They have to match too. Yeah, they just are going to equal each other. So the answer is simply a to the -1. I'm sorry, a equals -1. I don't say that quite right. Okay, so let's confirm with the calculator because it is a regular, common log. We can use the calculator to confirm, no problem. I want you to type log, parenthesis 1/10, and if we did it right, it should also tell us -1, just like we saw here. Did it work? Okay. Nobody told me it didn't, so I think we're okay. So there's 2 different ways to do it because it happens to be a common log. On part A, that didn't happen. We did not have 2 ways to do it yet. We will later. All right, similar kind of question on this one, but if you'll notice that the x is trapped inside of the log to start with on this one. What do you think you would do on this problem to solve it? Same thing. So Megan, tell me what should I do physically, like on my paper or on this screen? Okay, everybody good with that? Circled my 81 and I drew my tail. How will I rewrite this then? (81 to the 1/4 equals x). Now, I don't remember if I ever talked to you guys about fractional exponents. I just don't remember. It would have been an intermediate if we did it, but I kind of feel like I didn't. So just as a rule of thumb, a square root is the same thing as a power of 1/2. Okay? So what do you suppose a power of 1/4 would look like? Yeah, it'd be a 4th root. So a 1/4 power is the same as a 4th root. So we would take the 4th root of 81. That I know we've talked about. We would factor 81. How does 81 factor? Nine and 9, and the 9's factor as 3 and 3. So literally we have 4 3's underneath here. So what is the 4th root of 81? It's just 3. Good job. Okay, so we're going to shift our focus a little bit to graphing now. Okay? So the first thing I want you to graph is something you know how to graph because we've already been doing it in the last section. I want you to graph the equation y equals 2 to the x. And remember, when you do that, you should have 3 sets of numbers, 3 points, to plot. What x values would you most likely choose? Yep, 0, -1, and 1. If I plug in -1, what do I get? 1/2. How if I plug in 0? I get 1. And then what if I plug in the number 1? Yeah, I get 2. So if I go over here to plot these, it looks something like this. What's one other feature that would be potentially useful for us to plot? The asymptote. Keely, do you know where the asymptote would be? Y equals what? 0. Yeah, y equals 0, which is the x-axis. So I'll draw mine in red to try to just make it pop out a little bit. Okay, so is everybody good with that graph? Yeah, that's a good graph. Hang on. So what I want to do next is I want us to sketch the graph's inverse. Sorry. I didn't want these to be all in the same line, or all in the same stuff, so I wanted to copy paste them. Let's try that again. Okay, so how do we do inverses? It's been a while since we've actually graphed inverses. It was before your last test, so it would have been like over a week ago. The way that we graph inverses is that we draw the line y equal x, and we flip it across the line y equal x. So I'm going to put in the line y equal x. All right, something like that. So if I were to take this image and I were to flip it over that line, right, fold it along your curve, or along the y equals x line that we just drew, can you tell me what it would kind of look like? Would it, let's do this. Would it be increasing or decreasing? It would still be increasing. Where would it have an asymptote? What do you think? Not sure? The first graph has an asymptote on the x-axis. So we talked about when we did inverses, inverses are switching x's and y's. So where do you think this would have an asymptote? On the y-axis. Exactly. And so if I do a mirror image, like this point, for example, would become this point. This point would become this point, and this point would become this point. And when I connect them, it would look something like this, and my asymptote would be on the y-axis. Can you see the reflective nature of the two graphs? That graph that we just drew, that second one, is the graph of log base 2 of x. It's the reflection graph over the line y equal x. So that's where it's coming from. We'll talk about some features of it, but can you tell me what you see or you notice as the asymptote whenever you do that? We talked about it already. What's the asymptote going to be? The y-axis. What do you see the domain's going to be? This is the new equation I just drew over here, this one. What's the domain for this graph? What was that? It's not negative infinity to infinity. It's 0 to infinity. Yeah, we go to positive infinity, but it's 0, right? The yellow part that I just highlighted doesn't have any negative x values, right? It starts at the y-axis, which is x equals 0, and it goes to the right. Just the yellow graph. 0 to infinity. What's the range? Yeah, that's everything. That's negative infinity to infinity. Actually, everything switches. On the graph, I'll highlight it differently, but on the graph here at the top that I'm going to highlight, and we'll go with blue, this graph has a domain that's negative infinity to infinity. So our yellow graph's range is negative to infinity. The blue graph's domain is 0 to infinity. So my yellow graph's range is 0 to infinity. My blue graph has a line at the x-axis as an asymptote. So my yellow graph has a line at the y-axis as the asymptote. Okay? All those features just switched because x's and y's switched. So these are the features of our graph. This has a vertical asymptote, which is the y-axis. The y-axis is a line x equals 0. This is a graph of log base whatever to the x. Looks like that. So, I was going to draw that one first. Okay, so here's my asymptote. Through here. You'll notice that it has an x-intercept, and I tried to draw it accurately. I think it was pretty good. The x-intercept is actually 1, 0, instead of 0, 1 for the y-intercept. So this is 1, 0. We talked about the fact that the domain is 0 to infinity, and the range is negative infinity to infinity. Remember, domain is x values, range is y values. So everything switched. By switched, I mean the x and the y's. From the graph, y equals a to the x. This graph would be y equals log base a of x. It's exactly switched to x's and y's. All right, so the cool thing is that just like all the other functions where we can shift things left, right, up, and down, it works the same way. So if we're dealing with trying to find a graph based on already having a graph, so this blue graph you see here, it's essentially the same when we keep drawing. How stretched out and how narrow it is does change based on the base. Okay, that part does. But the features that we mentioned over here don't. The domain's the same, the range is the same, the x-intercept's the same, and the asymptote's the same. Okay, all that's the same. But we can still shift things left, right, up and down, stretch them out of shape, and compact them and all that kind of stuff using the same features we've seen before. So thinking about what we've done before, -3 on the inside, what does that do? It moves it right 3. Very good. And how about the 4 on the end? Up 4. Okay, so now on this one, moving things up and down would not change my asymptote, right? Because the asymptote's already vertical. So shifting a vertical line up and down doesn't make it look any different. But shifting it left and right would. So if I'm going to shift the whole graph to the right 3, it means that I'm also going to shift the asymptote to the right 3. So I'm going to start with shifting asymptote to the right 3 because it makes it easier to draw if I have the asymptote shifted. So this is my new kind of y-axis, if you will. And the ordered pair that we're given, I need to figure out where it's going to go. Well, it also is supposed to shift right 3, but it's going to go right 3 and what? Up 4. So right 3 moves it to here. Up 4 would move it to here. So that's the last point that I really need to plot to show that I've actually shifted things the way that I've been asked to. And then I'm going to sketch in the curve that I already had from before. I want to make sure the asymptote's still plotted and that the ordered pair, if they give me one, and this one did, also gets plotted accurately. Everything else is just a basic sketch. Don't need any other extra points. None of that was asked for. However, it did ask me to find the domain and the range. Now, that will change because I shifted it, right? I shifted up, right, left, you know, that kind of stuff shifts the domain. What's the domain for this particular function? Where do my x values start for the graph that I drew? 3. And do I get to equal 3 or not? So am I a parenthesis or a bracket? What was that? Parenthesis, because the asymptote actually happened at 3. The graph starts after that. And where will my domain sort of stop? Yeah, infinity. It kind of doesn't stop, right? Yeah. How about my range? -infinity to infinity. It goes from the lower part to the upper part forever. It doesn't do it very fast on the log function, but it still does it. It still does it. Okay, we're going to do another one. Same directions, basically. The difference is that it doesn't give us the original sketch to start with. So sometimes it might be easier to start with that original sketch. Would you like to try that for you first? The original sketch is always going to have the asymptote at the x-axis. I'm sorry, at the y-axis, I meant to say. And it has an intercept right here. Okay, so the original graph, I'm going to sketch in right now. In fact, I'll sketch it in red, just so we know that it's the starting spot. It looks like this. And that's sufficient. I'm good with that. Okay, the asymptote, the point plotted for the intercept, and the basic shape. Now let's talk about what some of these things do. I'm going to move from the log base 4 out, and the first thing I see is a negative here. What will a negative do to a graph when I multiply by a negative? It doesn't, well, it does affect the slope, but not the slope's steepness. It affects something different with the slope. What was that? I'm sorry, I can't hear you. Narrow or wide. If it were a coefficient number, it would, and that's where you're getting kind of the same thing that Megan's tracking on. Negatives are reflections. They either reflect things down or up, or left to right. Okay? If the negative's in front, which it is, it's in front of my log, it flips things that are down, up, and up, down. Okay? So this is a reflection over the x-axis because it's happening in front of the log. If the negative were inside with the x, it'd be a reflection over the y-axis, okay? Now this is a 2 in front, but it's the same as having a plus 2 at the end. What does plus 2 at the end do? Moves it up 2. This is just 2 added to my graph. So I need to reflect it, and I need to shift it up 2. You can do that in one step if you're so inclined. I tend to think that that's really tricky for me to do in one step. So I'm more inclined to move from the outside in and to do it in 2 steps, and I would reflect first. So to do a reflection would look like this. Up, down, up, okay? And then I need to take that graph and I need to shift it up 2. So my shift up 2 would put me here with that particular point that I had originally plotted on the x-axis. And it would look something like this. Now, even though I did all sorts of flipping things around and shifting it, none of that actually affected this particular domain and range, did it? It didn't. Because it's the shift left and right that would affect the domain. So my domain for this one is still 0 to infinity. And the range is still negative infinity to infinity. One last question. Are you ready? All right. No graphs on this one. And it's specifically just talking about domain and range. We know that the basic graph's domain is negative infinity to infinity. I didn't say that right. That's the range. Let me change that, sorry. Is 0 to infinity, and the range is negative infinity to infinity. But this one's different because it has something that's squared inside. Like, that's weird. That's not what we had before. So we got to figure out what is it doing to change that. Well, if you take a look at the graphs for log, you can only put in side of a log positive numbers. It's a domain issue. If you put your calculator and you say log -2, it's going to say error domain. That's what it does on mine anyway. That's the language my calculator uses. So in particular, what you need is you need the inside of the log, which this one is x squared minus 4. You need for it to be greater than 0, not greater than or equal to. You can't do that one either. Log of 0, it's going to say error domain. That's an inequality, and we graphed inequalities on number lines and checked these out once before. We did that by factoring, identifying that those happen at -2 and 2, creating a number line and testing points. If I test these points, I'm just going to jump to the thing that's really going to happen here for you. But if we test these points, you're actually going to get that this one is positive and then negative and then positive. And what part of this is it that we really need? Do we need the positive part or the negative part? Positive part, because it says greater than, right? So this piece and this piece are part of my solutions. So my domain is negative infinity to -2, and then 2 to infinity. But the kicker is, my range didn't change. It's just the domain that does. It's still negative infinity to infinity.